Welcome to this afternoon's panel. How can customers, DERs, and demand flexibility provide transmission and/or distribution system services? I'm Cristin Lyons, and I'm a board member at eSig. I also serve as an advisor at ScottMadden and with encoord. And I'm really happy to be here having this conversation with you all today. To get us started, I wanted to set a little bit of context for the history around these distributed energy resources actually providing services, whether it be at the distribution level or at the transmission level. So if we go back 10 years or so, we started to see these projects like the Brooklyn Queens Demand Management Project in New York come up with these ideas that said, we can avoid huge infrastructure investment. In that case, it was $1 billion substation if we use demand management and energy storage. And there evolved a model driven partly by the regulator that said, wow, if we don't have much load growth, we can defer some of these expenditures and save a lot of money for our customers. So we started to see these types of projects get woven into regulatory proceedings. New York Rev was one. We're seeing the same types of initiatives in Illinois. We've been seeing them in California for a long time. So the question started to emerge, not only can we use DERs to offset the need for infrastructure, but what other values can they provide to the T&D system? So we ended up moving into things like, back in the day, it was value of solar. That was some time ago. We've got value of DER. And again, stacking these values in a way that it makes sense for them to be compensated for the services that they actually provide. So importantly, when we started this conversation in the mid-2010s, we had low to declining demand growth. You know, we were looking at the ability to defer infrastructure for many years because we weren't seeing the load growth. And as you've heard over the last 2 days, and I'm sure we'll continue to hear through today and tomorrow, we now see huge load forecasts, you know, like up to 2030, I believe the number is 25% across the country. If you look at 2050, the number is closer to 80% load growth, which is, these are numbers that we have not seen, certainly in my lifetime and probably before that. So a few things have changed tremendously since this conversation started about the value that distributed energy resources may provide. Load growth matters in this conversation because the values can look really different. Second, technology is advancing very quickly in this space. So we're actually starting to see optimization and orchestration of these resources through things like DERMS. So the options for actually leveraging that value in the transmission and distribution systems are increasing. So to that end, I have a panel of experts up here who are prepared to talk about that and what they're seeing. Our first presentation is going to be by Ken Aramaki. He is the Director of Integrated Grid Planning, and that group includes forecasting, near and long-term resource planning, transmission, and interconnection planning. Our next, I'm sorry, I just messed that up. Obadiah is going first. So Obadiah is who I'll introduce next. Obadiah Bartholomy is the manager of distributed energy strategy at SMUD. And to the extent that you've followed what SMUD is doing, they're very much on the cutting edge of a lot of these conversations. Third will be Carlo Brancucci, who's the CEO of encoord. encoord is a software company that actually does integrated system planning all within a single platform. So there's an opportunity to evaluate transmission, distribution, and generation alternatives across one another in a way that's actually quite novel. And last but not least, Julieta Giraldez is a director at EPE Consulting, and she's a director of integrated grid planning. Prior to that, she was with Cavala, and prior to that, she was actually with the National Lab, NREL, if I remember correctly. So we have fantastic expertise up here. The last thing I'll say before I turn it over to Obadiah is thank God for pinch hitters. So if you read an early version of this lineup, only one person is the same. That was Carlo. So thank you all for stepping in. We look forward to your comments. And Obadiah, I'll turn it over to you.
Great. Thank you very much, Cristin, and thank you all for being here. I'm going to talk to you today about some of SMUD's experience integrating DERs into both our distribution and resource planning processes. And I'll start off with a little bit of context so that some of this makes sense. We are a utility serving about 600,000 customers in the center of California. And we have a peak demand of about 3,000 megawatts. Just to orient you a little bit to this chart, which is projecting out the growth in DERs that we're forecasting. You can see we're kind of here at 2025, which is a bit of an inflection point. We're starting to see quite significant growth in the distributed storage space, coupled with strong uptake of EVs that are going to be enrolling in our managed charging program. And we're starting to see glimmers of hope again in the V2G space as AC V2G solutions have now dropped in cost. We're projecting in the next couple of years, those are going to be starting to be adopted at under $3,000 installed. So that's kind of back in the forecast for us. So a lot of growth potential, a lot of resource potential for us to be thinking about both on the distribution system and on the bulk system, which is important because as we look out another decade, this is our forecast just for our EV growth. We have about 10 million megawatt hours of existing retail sales to our customers, and this is projecting nearly another 5 million megawatt hours of retail sales by 2040 just to electric vehicles. So 1 out of 3 kilowatt hours that we sell to our customers will be sent into an electric vehicle. That's a lot of growth to accommodate on our distribution system and really puts the importance on figuring out how to incorporate DERs effectively into planning to make sure we're not having to build our grid out another 50%. This is a quick snapshot of some work we did a couple of years ago on our medium heavy duty fleet expectations for the grid costs associated with that. That study looked out to 2041 and projected an additional cumulative grid cost, upgrade cost of 680 million to 1.2 billion over our expected investments over that timeframe all on the distribution system. That's 60 to 100 substations out of what we've currently got about 230 distribution substations. So about possibly a quarter to a third of all of our substations needing upgrades or expansion in 15 years, which is quite a dramatic challenge for us, both cost-wise as well as just figuring out where to put these. A lot of our area is built out already, so there is actually not physical space for us to go in and slot in new substations or expansions in some cases. So that really puts some heavy focus on managed charging. What are these charging profiles going to look like, as well as on DER solutions to be able to avoid these upgrades, and for our planning processes, figuring out how we can trust these DER solutions to actually deliver for us and be installed in a timely manner to avoid that capacity upgrading. So one of the ways we're exploring testing that is with a pilot that we are working on. This came from a subsequent follow-up study of those 60 substations I just mentioned, which cost about $5 million per piece to upgrade. We identified out of those 60, about 21 of those that looked like they would have a good chance for a modest amount of battery storage to actually avoid those upgrades, and for us to save about $50 million for our customers by doing that. And so we're proceeding with a program to attempt to demonstrate that. These are third-party owned batteries. We'll have about 7 of these 1 megawatt scale batteries that we are locating at commercial customers who are behind substations that are over 80% loaded. So not yet substations that would need to be in our budget officially for an upgrade, but they're close to it. And that figuring out which substations our CFO was willing to let us spend this money at was a bit of a process this year, given that these are not yet in the budget and there's some uncertainty on the timing of when will we actually need to upgrade these. We're effectively spending money that we might not have had to spend for another 5+ years. So getting, for us, without a state regulator, we've got kind of our local board who's a fairly hands-off, they determine rates, but a lot of these decisions have to get made in-house at SMUD. So it's convincing folks like the CFO that it's worth spending the money to get this learning and be able to do this to be ready for that wave of substation upgrades I mentioned. I guess one more quick item on the business model on this one. In order to make this something that we could do quickly, we knew we had to have this be quite a lucrative opportunity for the customer. So this is no cost to the customer. They receive a lease payment that's offset by bill savings sharing with SMUD. So our intention to dispatch is aligned to their retail rate somewhat. We're also looking closely at wholesale rates and distribution constraints in that optimization. The customer also receives the resilience value of these, and I mentioned the targeting. So hopefully that's going to lay the groundwork for demonstrating to our distribution planning team we can do these deployments in a timely manner, that the batteries will operate reliably, and we can replicate and scale this. I'm going to shift gears a little bit and talk about what's come now from a planning standpoint. I mentioned that medium heavy duty study. We're now in the midst of our third iteration of an integrated distribution resource plan. And this is a study looking out 15 years on our distribution system, forecasting all of the DER growth, electric vehicle growth, storage, solar, and attempting to understand what the total system impacts are associated with all of those together, as well as what the deferrable capacity opportunity is. So a bit more of a refinement of the two examples that I showed of the medium heavy duty and storage analysis with a more complete picture here. So this has been a lot of work on understanding the different charging shapes, as I mentioned, being quite important, different adoption scenarios, feeding into a spatial allocation tool within LoadSeer. And that's where we're going to do the analyses of understanding system impacts, following up with some DER optimizer work that I'll explain in another slide that talks about how we actually select DERs to avoid these investments and optimize the DER operations for serving distribution needs. So that DER optimizer is really attempting to take a number of inputs here, the baseline feeder load forecast, our distribution system upgrade options, what those cost and the sizes, what the DER supply curves are from a cost and capacity standpoint, and as well what the bulk system avoided costs are to feed into where should we put DERs, how much, what kind of capacity, and how should those be dispatched. And getting the baseline right here is really critical, because that then defines the amount of value that's potentially out there and kind of the scale of what the programs that my team is responsible for crafting need to try to accomplish over this time frame. So this slide speaks to some of the scenarios we're exploring. And again, a key focus on the EV charging behavior, how much charging occurs that's unmanaged, that is managed to our retail rates, that is managed to our bulk system real-time pricing, and how much vehicle to grid are we going to see over this time frame. So we looked at different blends of those between the reference case and a case that's actively managing to serve bulk system needs, as well as a case that's proactively managing to try and minimize local impacts. And yeah, definitely some unexpected outcomes so far in our preliminary results with E3. We're definitely seeing some winter peaking behavior that is surprising to us and is causing need for upgrades and timeframes we didn't expect. So we're doing some work to kind of troubleshoot that, but again, like getting these scenarios right is really critical for informing the scale of the programs that we're going to be launching and trying to scale up, as well as the value that we can offer to customers for those programs. So this is just a snapshot of a touch of the complexity that goes into this. These are some of the different shapes, both weekday and weekend, winter and summer, for one type of charging. This is heavy duty regional home-based charging. As you can imagine, there's a bunch of different profiles that go into this across the commercial space. I think we've got 7 or 8 different types of fleet vehicles and different profiles within those. different seasonal shapes. And then similarly on the residential side, quite a diversity of charging there between home, multifamily, workplace, and DC fast charging. So I'm going to wrap up by talking about how this feeds into the integrated resource plan. So I mentioned kind of getting that value right for being able to specify DERs as solutions on the distribution side. We're about to kick off our integrated resource plan, and there's a big question of how much should we count on DERs and with what types of behavior should be put into that resource plan. So we've kind of got three pathways here. The DERs are going to show up in that resource plan. The first one over on the right-hand side is basically coming in through our load forecast. And there we've got different scenarios that we have developed for customer adoption of each of these types of technologies and assumptions on shapes for charging as well as discharging things like batteries and vehicle to grid. Then the second path is for projects that get specified out of this IDRP as non-wires alternative case studies and estimating what the scale up of those will be, where those are just purely justified based on their distribution value. Those would go in as expected built resources or planned resources into the IRP. And then we've got the capacity expansion element in the middle, which is really looking at, I don't quite have enough value on the distribution side to make it a justified investment. And I don't quite probably have enough value on the bulk side to make this competitive against, say, utility scale storage. But if I can put those two value streams together, will the model specify this, and will distributed storage outcompete utility scale storage is kind of really the key question that we're trying to answer with that, and at what scale, as we're looking to really ramp up investment in the bulk storage space. So that's a quick snapshot of how SMUD is looking at DERs across these different planning domains. And I'm looking forward to the next panelist. So thank you very much for having me.
Okay, good afternoon. Ken Aramaki, I'm the Director of Integrated Grid Planning at Hawaiian Electric. Prior to this, which was about 3 weeks ago, I was the Director of T&D Planning. So I kind of have a perspective on the DER stuff. Our presentation's titled Expanding DER in a High DER System. For those that don't know, I mean, Hawaii's a pretty sunny place, so there's a lot of DER, rooftop DER. So Hawaiian Electric, we operate 5 of the 7 major islands in Hawaii. So the ones in purple, Oahu is our main load center. That's the one with the like the financial district. That has 300,000 customers, and then Maui County, which consists of 3 islands, and Hawaii Island. So total, we have about 450,000 customers. As of last year, our consolidated RPS was 36%. So 36% of the energy was provided by renewable resources. 16%, not 16% of that, but 16% was also provided by customer DER. And customer DER primarily is rooftop solar. Our adoption, so we have 114,000 systems as of last year. So that's, about 25% of our customer base, amounting to 1.4 gigawatts of installed capacity. For perspective, on Oahu, our peak load is, or peak demand is 1.2 gigawatts. 43% of single family homes have rooftop solar. And the other one is, last year, our 94% of rooftop solar was also installed with batteries. So because of our incentive programs, most of the rooftop solar systems come with batteries. So even though we're at these high levels, we still need DERs to continue to increase on the system, primarily to provide energy as we, go towards our objective of getting to net neutral or net zero carbon. So in our integrated grid plan, we have about 800 megawatts or so of additional DER that's needed on the system to get to 2050 timeframe. This is one example of how we of one program that was pretty successful in its subscriptions, and it's pretty simple. So we have a peak between 6 and 8. We created this thing called or scheduled dispatch program, but we marketed it as battery bonus. So customers who added a battery to their system would be provided an incentive of $8.50 per kilowatt at the start, and then $5 per kilowatt monthly. So that takes care of a pretty decent chunk of that battery installation. You know, on top of the federal and state subsidies, a lot of it gets paid off. We did do this ramping. So the systems, they're not controlled by Hawaiian Electric, or they're not dispatched, but they're set to dispatch at certain minutes on this curve. And so that happens locally, and then it does that so that it doesn't create like a step change on the system. The program that we have now going forward is basically a time of use or time of export type of program. So incentivizing customers to put in resources that also export at times that we want them to export. Again, we don't have really good controls or visibility onto on these DERs. So long-term planning for DERs. There's opportunities to help increase DER adoption. We have new customer programs. We're going to start bring your own device, just like, you know, many other utilities. The capabilities are going to continue to advance, so that's going to help. We think that we also need to get improved dynamic modeling so we can better understand how they perform on the system. And then that way we can also not get rid of, but, you know, any margins that we put in our modeling for uncertainty can also be reduced and maybe hopefully help increase DR. And then, you know, increase loads. We don't have like the crazy loads that everyone's seeing here, but we do have inquiries on data centers, but, you know, not to these gigawatt levels. Challenges. So what we see as challenges, equity is going to play a big part in this. Also market saturation. So we believe that, you know, the folks that have the wherewithal to put their own resources on their system, we're kind of reaching that max point already. So, you know, how do you get others to also put rooftop solar on their systems if, you know, they're not, they didn't prioritize that, I guess, before. And equity, because, you know, now we're going to have those that couldn't put this rooftop solar. Now they're taking the burden of everything else. Distribution, we're seeing hosting capacity upgrades being required on not just the distribution side, but now it's going up to the subtransmission. Some circuits, we are kind of nearing this point where, you know, putting anything DR utility scale on things connected to certain subtransmission is almost not allowable. There's going to be stability impacts. You know, DERs have, you know, ride-through impacts, momentary cessation. They decrease our EFLS effectiveness. Also, system hosting capacity on some of these, our smaller islands, we have situations where the generators are running at minimum loads. So, like, we can't take any more on those islands. Reliable operation and cost-effective controls. We don't have a good system for that today. And that's basically what we need to kind of further enhance and increase DR. And then the other unknown is advanced inverter capabilities and how that will impact other parts of the system. We're working on getting a new category 4 in a new category 4 under the IEEE 1547 standard. What that does is it helps to keep the DER running at low voltages and, tries to address some of the ride-through issues and momentary cessation. But the unknown is, how does that impact protection, at en masse protection, power quality? Is the anti-islanding system going to actually work? Things of that nature. That's it.
Oh, thank you.
Thank you.
Good afternoon. Thank you very much for the invitation, Izig, and thank you, Cristin, for moderating and the introduction. What I'm going to be talking to you today is how can we benefit from an integrated planning approach in systems that either already have significant amounts of DRs or systems where we do expect growing penetrations of DRs. And I guess we can assume that any system in the world that is true, even in places that are not very sunny, but where we are seeing the penetration of electric vehicles or heat pumps or other potential flexible demands in the system. First of all, I want to talk about how distribution planning is really getting harder. I've never been a distribution planner, but I keep hearing it from many of the utilities we interact with, as well as just from driving around my neighborhood and seeing how many electric vehicles there are, how many people are putting rooftop PVs, how many people are putting a 20+ kilowatt instant water heater in their home or heat pumps. So a distribution planner in year 2000, or maybe not that long ago, just a few years ago, really thinks about planning the system, ensuring the reliability, the power quality of its distribution networks, and ultimately defining what are the infrastructure upgrades required to maintain deliverability of power, reliability, and power quality. And most times distribution planners have thought about peak demand. They designed the system to meet the customer needs during peak demand. They designed a system that observed only unidirectional power flow. They treated the substation as let's say, an infinite source of power, and they treated their customers as passive entities that didn't really contribute, and they will just consume power when they needed it. But that has significantly changed over the years and continue to change. And today, a distribution planner needs to think first about multiple loading conditions that may be greatly impacted by the rooftop solar PV that, for instance, they are observing tremendously in Hawaii, about how that may impact backfeed. You may now have situations where distribution feeders are generating more than they're consuming, so they could potentially backfeed into the transmission networks. They need to consider the behavior of the customers that not only have all these flexible and responsive devices, but they have different interests and different behaviors that will impact tremendously the state of the distribution network. And most importantly, they need to deal with DRs. And what I mean by DRs here is really rooftop solar, storage, and any type of flexible demand. And probably the most obvious ones are going to be electric vehicle charging and potentially controllable heat pumps. And to really understand how much are DRs really meaningful today, I always hear, well, there is only a few regions where there is a lot of DRs. Yeah, Hawaii is not really representative of the rest, of most of the power system, especially in the United States. So we did some internal research, and this is just based on public information. And we looked at, and these numbers are approximate, so don't take this for granted. And by the way, after looking at the slides of Ken, I think the HECO number is an underestimation, at least based in Oahu. The DR penetration as a percentage of peak demand of the entire system. And obviously Hawaii is the highest, as we would expect, but we have systems like ISO and ISO New England, where we have more than between 20 and 30% of the total peak demand of the system, there is equivalent capacity of DERs of different kind. That doesn't mean that obviously they're going to cover 30% or 20% of the demand, but that's potential flexibility that the utilities, the system operators can leverage. So, and that number is just going to keep growing. So it is a significant source of one, flexibility, and two, of challenges and worries to think about. Now, at encoord, what we do is we focus on integrated planning. We develop software for utility system operators or other to perform integrated planning. And what we mean by that is really helping people coordinate planning processes that traditionally have been done in silos and have been performed by different people, different teams with different expertise for different planning objectives and using different modeling and planning tools. DER is one of the most important drivers to integrate planning across traditionally siloed planning processes such as generation, transmission, and distribution. If I was a generation and a resource planner at a utility that is observing DR penetrations or is expecting large DR penetrations, the first thing is I'm going to think about is how will DRs impact load shape? I may be used to a system that peaks in the evening and I'm planning my generation, bulk system generation and storage to meet that. But with the penetration of DRs, that could change. I could have my system could start peaking at a different time of the day or a different time of the year, and that will have enormous impacts on the choices I make in the resources I want to acquire to meet my demand in the future. Or I'm going to wonder how much do these DRs contribute to resource adequacy? How much are DRs going to impact the amount of firm capacity I need in the system to meet my demand? Because they may have a major impact on energy consumption over the year, but they may have a different level of value from a ELCC perspective. And then if I'm a transmission planner, I'm going to worry about DRs even more because DRs may respond to electricity prices where they are allowed to or incentivized to do that in ways that may shape enormously the demand in different parts of the system. I'm planning for a transmission system that serves a larger region with probably very diverse sets of DR penetration, depending on the type of load that different substations are serving, and that can have a major impact on how load will change during different periods throughout the year. And the other thing is, how will DRs impact the reliability of my system? One is, how will DRs respond to a fault in my system or to a major change in my system or to a contingency? Will they ride through, or will they all respond at the same time and fall offline and exacerbate the potential contingency I have to deal with? Or will DRs impact upstream voltage profiles? Well, there hasn't been a lot of focus on the investigation in the Iberian blackout at the end of April. One of the speculations that people talked about after the blackout is how did the distribution network impact voltages? The blackout in Spain, in short, had a major over voltage component. Cool scenarios where DRs increase voltage in parts of the system end up in creating reliability challenges for the bulk power system, not just localizing in the distribution network. And then, as you know, a transmission planner traditionally plans for the reliability of the system during snapshots of time, usually during peak demand periods, shoulder periods, other operationally challenging periods. Well, these challenging, the variability of the operation of the operational conditions of the system continues to change because of the penetration of renewables, the penetration of storage, the penetration of large demands in the system, but it's also going to be potentially impacted tremendously by the behavior of DRs and how these are incentivized. And the other thing is a DR may behave in a certain way today, but as the utility programs change, a DR that in a transmission planning model impacted load at a given substation in a certain way, 2 years from now, rate programs change, and now that DR may have a significantly different impact on the load and on at a substation, and how that can impact transmission planning studies and ultimately the reliability of the power system. So as the grid transforms, we believe that integrated planning is really key to delivering reliable, affordable power under increasingly complex conditions. And planners are really challenged by the traditional planning process. And the reason is most planning processes, obviously a lot of them are developing, but it is still the case that many of the planning tools and processes and the analysis that are conducted were designed for a different era where DRs were not a thing or were very, very minimal. As those change, that's going to create a challenge if we still use processes that are built for a system that doesn't have DRs. The other challenges we just discussed, DRs doesn't only impact distribution planning, it also impacts transmission and generation planning. And those, in many cases, are done still in silos. And the other thing is, as these silos have evolved over time, what happened is every planning area, every planning team is using different data and assumptions to plan the same systems, and the tools they use, they were not designed to talk to another. So that's why integrated planning processes, we believe, and tools can really solve this challenge by helping plan for a modern, complex grid that has growing penetrations of DRs, can help coordinate across planning functions, and can really help assess the system as a whole through a unified platform and process. So at encoord, we have developed SAINT, the scenario analysis interfaces and integrated planning software. And one of the key use cases of SAINT is to really enable an integrated DR planning workflow. And as part of this workflow, if you were, and I'm going to focus as you were a transmission and distribution utility, or a utility that plans for both transmission and distribution. What a tool like this allows you to do is, first of all, model the transmission system as you've traditionally done with many other transmission planning tools, and evaluate the reliability of the system, power flows, voltage across different conditions, and evaluate potential transmission investments required to maintain the reliability and serve load at all operating conditions of the system. The other thing it allows you to do is, for the first time, really visualize that transmission system and the distribution system in a single unified model. So now you can represent your high voltage, medium, and low voltage part of the system in a unified data representation and over a map, and that is key. Planners often use their engineering judgment, but also their intuition. And being able to understand where a distribution network connects to the transmission network and how that relates to the rest of the system is incredibly powerful. And that intuition today is very hard, because there is very few cases where you can visualize your transmission network and its relevant attributes overlaid with your distribution network, and be able to run models where you change assumptions and see how the system reacts to the change of those assumptions. The other thing is ability to combine transmission and distribution reliability analysis together. So to understand, for instance, how will the response of a series of DRs or a virtual power plant impact reliability upstream, especially when you're starting to have DRs in a given region all respond in correlated ways, and potentially impact the sub-transmission or even higher transmission system in its vicinity. Jointly optimized systems and DR operations. So DRs are going to, as DR penetrations increases, they're going to have an impact on how you dispatch bulk power system resources. So an integrated tool like this that can represent transmission and distribution networks will allow you then to not only run physical simulations of the integrated system, but you can actually run operational optimization models of the integrated system and see how DRs respond in conjunction with or in response to the bulk power system or the electricity market they are connected to. And finally, you'll be able to really compare cost and reliability impacts across different DR strategies, across different DR programs, or across the value of certain maybe utility-owned DRs or utility-controlled DRs, like examples such as what Obadiah mentioned before, using behind-the-meter batteries or behind the substation batteries to displace the need for a substation upgrade that could have major impacts also on the upstream transmission system. And I want to end with one slide looking at a project we recently completed. This was a proof of concept project looking at the unified modeling of the transmission and distribution system in Vermont, and looking at how virtual power plants or aggregations of DRs can impact grid reliability and the flexibility of the grid at the grid edge. This is a project we did with VEC, an electric distribution utility in Vermont, Valco, which is the electric transmission utility in Vermont, and then with Elevate Energy Consulting. What we did here is we integrated Valco's transmission planning model. We carved out the Vermont transmission system from the Eastern Interconnection model, and we defined boundary conditions to properly represent it for the purpose of this study. And then we hanged off 3 major feeder networks under 3 substations. And then we populated with AMI data and other information from VEC all the DRs in those substations. So that included solar PV, storage, EV, charging, chargers, and heat pumps. And then we looked at how could you leverage the flexibility of those DRs to impact and respond to transmission network needs. VEC customers have been experiencing electricity. I mean, why does it all matters? Cost and customers. VEC customers are experiencing rate increases that are primarily driven by transmission upgrades. At the same time, VEC is experiencing a lot of DR penetration, and the question is, can we leverage some of these supposedly flexible resources to potentially minimize some of the required transmission upgrades that at the end of the day, those same customers are going to have to pay for? So we looked at, can we leverage DRs to reduce or avoid or displace, delay transmission projects, and especially how can we leverage DRs during transmission contingency events? So it was a very excellent opportunity that really integrated the transmission planning models and planning process traditionally done at Valco with the distribution planning process done by VEC. And what I'm very proud of this 4-entity collaboration is this is not an integrated T&D utility. Here is 2 entities. Obviously, Valco is owned by VEC and other utilities, but they're still different entities, and we were able to collaborate and build an integrated model. So if that is possible with 2 entities, I think it's absolutely possible to do it with entities that actually operate both transmission and distribution networks. So thank you so much, and I'll welcome any questions later. And before I end, I just want to, there is a lot of people in the audience that contributed throughout the first half of this year and the second half of last year to the Integrated Planning Task Force at ISIG that led to 3 major integrated planning documents that have been published in June. The encoord team was highly involved in the Integrated Planning Guidebook. That working on that guidebook has really helped us learn from a lot of generation, transmission, and distribution planners in the industry that has ended up really helping us at encoord understand the challenges and the needs to integrate planning processes at encoord, and has definitely helped inform the project, for instance, we did in Vermont. So thank you all that contributed. And if you have not looked at the guidebook or the other integrated planning documents that ISIG published, I highly recommend it. They're public on ISIG's website. Thank you all.
Hi, everybody. I'm Julieta Giraldez with Electric Power Engineers, Director of Integrated Planning. I am part of that great Team B, replacing Team A, originally in the panel. So I'm the obviously better version of Lavelle Freeman that unfortunately couldn't be here from Eversource. And I was asked yesterday to come up here, and somebody said, well, just put an image of an adorable kitten and talk about integrated planning. You can do that all day. I was like, well, that might be a great option. And so I did that. The first funny thing about that is that I went to AI to create an image of an adorable kitten, as if I couldn't Google, like the old days, adorable kitten. And so I was like, well, that's silly. I'm just increasing the demand for something I don't need. What might I need AI to create an image for? And so I asked AI to create an image of the adorable kitten planning with his friends, the puppies, the squirrels, and the rabbits. And I thought that would be more appropriate, and I needed AI for that. And this is what it came up with. And so I'm actually going to put the fellow panelists and the moderator on the spot here and look at the image, because I thought there was some interesting things. I just tried twice, so this is the second try, and I was pleasantly surprised with the result. And so I was going to ask you guys if you can tell me two things that utility planners today cannot do that our friends, the kittens, the puppies, and the squirrels in that image can. So Obadiah, Ken, Carlo, Cristin.
I'll offer one, which is,
There you go.
yeah, I'll offer one, which we were lucky enough to have EPE come in and host a workshop for all of our puppies and kittens and within SMUD last month. And that was the first time we all sat around a table together and worked on this topic together. And so I was really pleased with that. And obviously they're doing that nicely there. So
Excellent. That was going to be my third. So right on. Ken?
I would say they probably haven't used a ruler in years.
That's a good one.
I see a kitten that is voluntarily sharing its results, which I have rarely seen amongst utility planners.
They're not hiding them.
Correct.
That's a good one. Carla, do you want to take a chance?
I imagine these animals have higher visibility than maybe many planners have into their own system.
There we go. There we go. And you gave already some good hints, with your what you guys are working on. But these are the things that stood out to me. And then the third one was the one that Obadiah mentioned, which was they're all of them together, right? Looking at the same thing. So everyone's looking at the same map. That is something that we cannot do today, 2025. You go into any utility or region, folks are using different data set maps, softwares to look at the grid. The second thing that I thought was really cool, this came up with, it was the magnifying glass. And that's something that we are currently struggling with when we're doing planning and grid planning, is that need for higher resolution, locational and temporal resolution, and this struggle between going from the big picture to the small picture, right? Or you're either planning a substation, a feeder, you have everything, you spend a lot of time, or you're doing a system level. But we have a really hard time going between both. So good job with AI for coming up with this image. And I think this is what we're working towards, right? A platform and processes and organizational really change towards this. One of the other things that we still cannot do in 2025, which to me it's still stunning, because I was able to create this image with AI, but we still cannot agree, and within a utility, within the same organization, or among a region, what is the state of the current grid today, right? What is the data? If I would say what happened in 2024 for planning, distribution is going to have one answer. They use SCADA for that. transmission is going to use system level zonal data. The financial and customer planning department is going to take billing data. Still, the dream of having horrible 8760 database that we all pull from, and we can, take different grid points and decide that I want the coincident peak demand here or the non-coincident here. That is still a dream. While I can create this image with AI, we still cannot agree today to what the state of the grid is. And we heard this from the market operator in Europe yesterday. They were saying that one of the biggest challenges with the Iberian blackout is just to get the data of what happened, let alone agree on what the future is going to look like, right? So forecasting is still one of the key, I think, aspects of integrated planning, where you're going to find different answers within the same organization or among different organizations to what the future is going to look like. And definitely, the topic of today is integrated planning with DERs. And DERs are definitely challenging for good. I think our need to integrate and coordinate, right? So they are challenging what the future demand is going to look like, what the generation, the effect, what we should plan for, and Obadiah presented a little bit on that. They're going to affect the infrastructure that's needed to be planned at transmission and distribution. And it is ultimately a lot of that led by customer choice. So we can't forget that we need to understand customers and their behavior in all of this. But I do have some slides, so we're going to get serious. And what I'm going to talk about here is one of those key aspects, I think, to understand DR in all of the planning domains is what is the DR value. And for that, we've heard a little bit about the need to understand all of the value stack of DRs, right? So we know now that they affect, as I was saying, the generation needed, the T&D infrastructure, and we've been working a lot with utilities in trying to understand and have a common model to understand all of these value stack. Typically, just when one planning domain looks at DR value, it is not sufficient for whatever business case they're looking at, or they have conflicting business cases. And so it's really important to look at this as one. The one that I'm going to focus on is the bottom one, the locational value of DR. It has been, I think, the hardest one to tackle. There's been a lot of generic models, average values used, but it doesn't work that way, right? We need to understand really that magnifying lens that I showed on the image, substations by substation, feeder by feeder. What are customers planning to do there? What does the specific infrastructure look and the demand to understand the value? And so this locational value of a DR concept is the way I like to explain it is imagine you are, a distribution planner and you are planning for the future grid. What you typically do is you look at capacity, right? When is the peak demand? You typically, as Carlo mentioned, only look at peak demand on that specific substation, feeder, or piece of infrastructure. And you're going to look at when that is going to be a constraint to see if you need to plan for infrastructure. And so the question is, imagine you also can affect the demand. You can control the size, the location, and type of DR. Where would you put it and how would you want it to behave? That's the question that we're trying to answer with the locational value of DR. And so ideas of that is, you would go to areas with load capacity needs, try to identify where you can reduce peak load. You understand it's really important when you're planning for these resources and you're trying to understand the value, when are the needs gonna occur and what the certainty of that need is. And And then the other thing is that you can also look at hosting capacity constraints. So not only when you might need to replace the infrastructure because of load growth, but also where might there be areas where there is, for example, a lot of PV that is causing technical issues on the system, and you might want to incentivize other types of DRs or load to come on your system. And there is an overlap between the locational value of DR analysis and the non-wires alternatives that you might have heard. But what it's different, the way we see it, that it's becoming to become different in the way utilities are thinking of implementing, is that non-wires alternatives are sort of a procurement from the utility for an alternative solution to an existing problem, right? And so you need all of the confidence in your solution to replace that one piece of infrastructure. The value of DR concept is, I think, a higher level view of compensating or incentivizing the resources in the right areas to defer future capital investments, but also reduce the risk, right, of your scenarios or uncertainty in your planning. And so some of the utilities are using that locational value of DR analysis to inform an NWA procurement, but also to do what Obadiah is doing, right? To collaborate with the customer programs and DR planning department to design programs to incentivize the resources in the right place. And if you think about it, this starts to look a lot like a distribution system operator concept, right? So we see it as a planning precursor towards a more active distribution system where you are controlling and orchestrating the resources. And the way we've seen it implemented, some utilities, for example, are thinking of revising NEM, so the compensation mechanism right now in most of the US, the customer, there is the same compensation independent of where you are in the grid or the size of your DR or anything. And the way some of utilities are thinking is, designing a floor compensation, but then incentivizing where they want the resources that are most beneficial to the grid. So it is important to tailor this analysis towards what the different DRs can do. And so these are, for example, types of DRs that will have different values. They operate in different ways, and it depends really on the resource, whether it's controllable or not, the size, and many other things. So these are, for example, values for different DRs that we have worked with utilities in understanding. So solar, energy storage, but also flexible load and electric vehicles. And it is important. The idea is that you start, for example, you might have an area that is already saturated with PV, and the contribution of the PV to the peak load is no longer happening. Your peak load might have shifted from the late afternoon to the evening. And so in that area, more PV alone is not necessarily going to provide benefits to your grid. And so that area you might incentivize, for example, flexible load or storage or electric vehicle charging in order to start affecting the shape of the demand for the distribution system. And I think it's something that just in general, distribution planners have not had as a tool, and they don't have really the tools to understand it. So we're working with them in helping develop these processes. But we've discussed this quite a bit with Obadiah and others. The concept of utilization, right? In distribution system, we typically just care about that peak load. We don't really care about the AVD 760 behavior, but it is really becoming a key part of understanding DRs across all of the planning silos. So in order to do this, it looks very similar to what other presenters have shown. We understand the load growth forecast. So the value of the different resources in a system are going to depend on what we think is going to happen in the future. The substation loading, the equipment, when the upgrade project costs, and also are there other technical constraints that can be addressed by these DRs. And so it ends up looking a little bit like this. This is, I think, how Illinois was thinking of deploying it, is sort of a hosting capacity map, but instead of saying how much of a resource you can interconnect at that point, you are providing incentives. So you would imagine each one of those squares is a different value for how much you're going to compensate a DR in an area versus another one. So you can start affecting the way you want the customer and the 8760 loading ultimately to look at. That's the idea. And these are some of the sample results. So you can see, there's a lot of acronyms, but you can see that you have different types of DRs. So behind the meter, front of the meter, PV and storage. And then you can stack that locational value in a specific feeder and a substation with avoided transmission costs, as we saw at the beginning, congestion, and also generation. And you end up with that value stack. So what does success look like in understanding DRs across the integrated planning domain? So as I said, I think it is very important to really push utilities for the need to have shared data sets across the silos, making sure that those puppies, kittens, and rabbits that I showed in the first slide have a shared understanding of what we have today, what we're looking at today, and what we're going to look at tomorrow. I think that is really key to make teams understand each other. And then I think the other thing is that there is a lot of potential to understand that flexibility across the silos. So I forgot to mention at the beginning, but we are working on an integrated planning Power and Energy magazine issue that's going to come out next summer in 2026. Actually, in one of the articles, all of us up here are collaborating. So encoord, SMUD, and HECO. There is a lot of talk about flexibility being one of those sort of cross-cutting needs that are that we need to understand across generation, transmission, distribution, and customer planning. But I think I'll leave it at that. And following what Carlo presented, the need for everyone to look at the same map and the same data as a key driver to better integrate DRs in the grid. Thank you.
Thank you so much.